Welcome to problem solving session number 4. In this problem solving session, we are going to do a couple of problems based on our previous lectures, lecture number 10, 11 and 12. The first problem goes like this. Consider a composite system A plus B described by the state vector as it is given. Now here, as you can see, the state vector is written in such a way it is specifically saying which qubit belongs to what. Say 0 belongs to subsystem A, 1 belongs to B in the first term. In the second term, 1 belongs to subsystem A, 0 belongs to subsystem B. You are asked to find the reduced density matrix corresponding to subsystems A and B. Then you are also asked, is A and B are entangled? So let us solve this problem. To solve this problem, first of all, as you know, what we have to do is to find out the density matrix of the complete system. For the composite system, the density matrix is going to be rho is equal to k psi bra psi, and if I write k psi 1 by root 2 k01 minus k10. Now I'm not specifying subsystems A and B. As you can understand, the first term here belongs to, first one element belongs to subsystem A, second belongs to B, first belong to A, second belong to B, right? So that is understood. And the bra of bra psi is going to give you bra 01 minus bra 10. Okay, now let me open it up. So you will get rho is equal to 1/2. You will have k01 01, okay, minus k01 bra 10 minus k10 bra 01, and you will have plus 10 bra 10. So this is the density matrix for the composite system. Now to find the reduced density matrix of the system A, we need to trace out B. So rho A is going to be equal to trace over B. So if you trace out B, what we'll do, we'll take trace over the subsystem B only. So let us take out, just look at this particular term. Let me take out the elements belonging to subsystem A. So that would be k0, this one and this one, k0 bra 0, this belong to subsystem A. Then let me take the trace over the elements belonging to the subsystem B. So this is what I have. Okay, then let me do the next term here. Then again we have k0 bra 1 here, and trace is going to be taken over k1 bra 0. And now third term is we k1 here bra 0, trace over k0 bra 1, and finally the last term, that would be k1 bra 1, trace over k0 bra 0. Okay, so now already we know that if we take trace over k1 bra 1, this is going to simply give me the scalar product 1 1, and that is normalized, it is equal to 1. Similarly, this one is going to give me the scalar product 0 1, and this is going to give me 0. Here it would be scalar product 1 0, they are orthogonal, so this is going to give us 0. And finally this term, it would be scalar product 0 0, and that is equal normalized, so that is equal to 1. So we'll be left out with 1/2 k0 bra 0 plus k1 bra 1. So that's the reduced density matrix for the subsystem A, and this I can write in the matrix form like this: 1/2 1 0 0 1, right? So this is the density matrix for the subsystem A. Similarly, we can work out the density matrix for the subsystem B, and if you do that, you are going to just have to take out trace over the subsystem A, trace out system A, then you will get the density matrix for the subsystem B, and you will get this result 1/2. It is very easy to do. You will get K0 bra 0 plus K1 bra 1, and in the matrix form this is going to be 1/2 1 0 0 1, right? So this is what you will have. So now we have the density matrix for the subsystem A as well as subsystem B. Now the next question is whether these two systems are entangled. So to do that, let us just find out what is rho A square, that is the what is the square of the density matrix corresponding to the subsystem A, and that would be 1/2 1 0 0 1. That's the density matrix for the subsystem A. Take the product with itself, 1/2 1 0 0 1, and matrix multiplication is going to give you 1/4 1 0 0 1. This is what you will get as a result of the matrix multiplication. Now if you take trace of rho A square, if you calculate, that is the sum of the diagonal elements, you are going to get 1/4 plus 1/4, and that is equal to 1/2, and which is less than 1. And similarly, it is quite obvious that you are going to get the same result for the subsystem B as well. Trace of the rho B square, if you calculate it, it is also going to be give you 1/2, and which is less than 1. So this means that both these results means both subsystems A and B are in mixed state, right? A and B are in mixed state, and that implies that A and B, this implies that A and B are entangled. A and B are entangled. Okay. Now this was an easy problem. So now let us do another problem involving reduced density matrices, and this time let us consider a composite system A plus B described by the state as it is given here. You are asked to find the reduced density matrices for each subsystem. Are the subsystems entangled? So let us work it out. We can work it out in the similar way, and to do that, first of all, again let us find out the density matrix of the full system, that means the composite system density matrix. Now first of all, let me write down the state of the composite system in a little bit simpler form. Now here it is what is given, so let me write it as 1/2 root 2, and if I multiply this with this bracketed term, I will get 0 0 plus root 3 0 1. Okay, so as usual, the first element belongs to subsystem A and second one belong to subsystem B, and so on. And then from the second term here, I am going to get root 3 1 0 plus 1 1. Okay, so this is my state vector corresponding to the subsystem A and B. Now corresponding density operator would be K psi AB bra psi AB. So if I open it up, so what I'm going to get, let me write down all the terms. You can do it, it's simple. You will get 1/8, and you will get 0 K0 0 bra 0 0. You have to do it carefully. You will get second term would be root 3 0 0 0 1, root 3 0 0 1 0. Then you will get 0 0 1 1. You will get lot of terms, so let me write all of them. You will get root 3 0 1 0 0 plus 3 0 1 0 1, and then you will get plus 3 0 1 1 0. I will urge you to work it out along with me. You just pick up your pen and pencil and pen and paper, I mean to say. You should be able to do it. K01 bra 1 1 plus root 3 1 0 0 0. Then you will have 3 1 0 0 1 plus 3 1 0 1 0 plus root 3 1 0 1 1. Okay, then you will get K 1 1 bra 0 0 plus root 3 K 1 1 bra 0 1 plus root 3 K 1 1 bra 1 0, and finally you will have K 1 1 bra 1 1. So this is what you will get. Now to find the density matrix for subsystem A, we need to trace out B, and as you have already learned how to do that in the previous problem, let me write it quickly. So I have now row A, density operator for subsystem A. I have to trace out B. So trace, I have to take over the subsystem B. So this is going to give me 1 by 8, and you can figure it out. It's very simple. So you will get the terms like this: K0 0 bra 0 0 plus root 3 K0 bra 1 plus 3 K0 bra 0 plus root 3 K0 bra 1 plus root 3 K1 bra 0 plus 3 K1 bra 1 plus root 3 K1 bra 0 plus K1 bra 1. So this is what you will have, and if you let me simplify it, you are going to get 1/2 K0 bra 0 plus root 3 by 2 K0 bra 1 plus root 3 by 2 K1 bra 0, and you will get finally K1 bra 1. Alright, so this is what you will get, and you can now easily write down the matrix form, and that is going to be, so this is the matrix representation of the density matrix for the system A, reduced density matrix for subsystem A, and this is going to give you, here you will have 1 root 3 by 2 root 3 by 2 1. So I hope you see, you know how I have written it. You see the bases are, now this is a composite system, bases are 0 0 0 1 here, then I am writing here 0 0 0 1, right, in the column. So that's how I can this you just have to keep it in mind, this part you just have to keep in mind, and then you can easily write it down. So it's very easy to apply this, and you always just need to remember this trick, and we have actually discussed it many times. So this is the density matrix for the subsystem A, and similarly you can work out the density matrix for the subsystem B as well. And in fact, let me just give you that result, and it is going to be exactly the same. If you do the calculation, it would be 1/2. In fact, there is also a 1/2 term is there, so it is 1/2 1 root 3 by 2 root 3 by 2 1. So this is the density matrix for the subsystem B. Okay, the next part of the question was to decide whether these subsystems are entangled or not. To do that, the procedure is to calculate rho A square. So if you calculate rho A square, so you will get here 1 by 4, and just you have to make the matrix multiplication of this Here you have root 3 by 2 1, and again multiply it with 1 root 3 by 2 root 3 by 2 1. Okay, if you do the matrix multiplication, you are going to get 1 by 4 7 by 4 here, root 3, please do it yourself, root 3 7 by 4, please verify. This is what you will get. So therefore trace of row A square is going to be equal to, if you just add the diagonal elements, then it is going to give you 7 by 8. Okay, that's what you will get, and that is less than 1. And exactly the similar way, and obviously the trace of row B square is also going to be 7 by 8, and that is also less than 1. So this implies that both subsystem A and B are in mixed state. So it is clear that A and B are entangled. Now let us work out some problems involving quantum gates. As a first problem, consider this one. Find the output state for the following quantum circuit if the input state is 1 0. Now as you can see from the diagram, this quantum circuit consists of 3 gates. First is the X gate, followed by C naught gate, and this part, as you can see, this is the C naught gate, and is followed by another X gate. So this quantum circuit consists of 3 gates, and the input state here is 1 0. So let us solve this problem, and we are asked to find out what is going to be the output. So to do that, it's very easy. Let us do it methodically. So first of all, 1 0 is the input, so that means that this gate 1 is applied on the first line, and gate 0 is applied on the second line. Now the first qubit, that means gate 1, is encountering X gate, so therefore at the output of this X gate you are going to get gate 0. Now this gate 0 will act as a input, and this line, the second qubit will remain as it is not encountering any gate as yet, but then it is encountering this C naught gate. Now as you know, in the case of the C naught gate, this one is the control, the first line here is the control, and this one is the target. Now in the target you are having gate 0, and in the control you are having gate 0. Now as per the property of the C naught gate, its operation goes like this. As you know that the target is not going to get flipped if the control is 0. So at the output of this C naught gate you are going to get gate 0. Now this is going to act as a input for the next gate, which is the X gate, and as there is no gate, nothing else is there in the second line, so gate 0 will remain gate 0. So it will, at the output you are going to get gate 0 here, but this because of the presence of the second X gate, this gate 0 is going to get inverted, it is going to get flipped to gate 1. So therefore output state that we are going to get is simply 1 0. Okay, so now let us do another problem. Given the quantum circuit, find the output state if the input state is 0 1. Now you see here in this quantum circuit, it has actually 4 gates. One is the Hadamard gate, that is followed by C naught gate, and then you have a Z gate and Y gate. I will explain what is Z gate and what is Y gate. So let us solve this problem. So first of all, as you have the input state is 0 1, so that means in the first line the input is going to be gate 0, and in the second line the input is going to be gate 1, right? And first of all, it is going to encounter, the first qubit is going to encounter the Hadamard gate, and as a result at the output, because of the Hadamard gate converts this gate 0 to superposition of gate 0 and gate 1, equal superposition of gate 0 and gate 1. So this is going to be the output at the Hadamard gate, and the first line is not encountering anything as yet. Then it is going to encounter this C naught gate, and in the C naught gate what we are having is this. So for the C0 gate, let us see, for the C0 gate, the input is K0 in the first line and not K0, it is basically a superposition of 0 plus 1 by root 2 in the first line, and in the second line you have gate 1. So therefore overall the output is basically actually the state, that is input state, that is for the C0 gate is 1 by root 2. I can write it as 0 1 plus 1 1. Now as per the property of the C0 gate, again here you see this is the control, 0 is the control and 1 is the target, and here 1 is the control and 1 is the target here, and the target qubit is going to get flipped provided the control qubit is 1. So at the output here you are going to get, as a result of the output, you are going to get 1 by root 2. The first one will remain as it is, 0 1, the first one, because the control is 0, the target is not going to get flipped. But in the second one, because that control is 1, the target is going to get flipped, it would be 1 0, right? So this is now the state after this C0 gate. After this C0 gate, we have a Z gate. In the Z gate and Y gate are there, and both of them are single qubit gate. So Z gate is going to act on the first qubit only. So therefore if you look at this state here, 1 by root 2, after C0 gate you have the state 1 by root 2 0 1 plus 1 0, and now this is going to encounter the Z gate, right? It is going to encounter the Z gate, and there is nothing in the second line, so it is going to be the identity. So this Z gate is going to act on the first qubit only. Now what is a Z gate? Z gate operation is defined as 1 0 0 minus 1. Okay, so therefore what's going to happen? So if you have K0, if it passes through a Z gate, it is going to it will remain K0. But if it is 1 or whatever it is, if the input is 1, then here it is going to become, okay, let me explain it in a more clear form, what is the operation of Z gate and Y gate. So to do the Z gate operation, let me explain you it by using the matrix operation. So first of all, when Z is going to operate on K0, I can write it as 1 0 0 minus 1 for Z gate, and for K0 we have 1 0, and if you do the matrix multiplication, you are going to get, here it would be 1 and this would be 0, so it is going to remain 0 only. And when it operates on 1, so you are going to get 1 0 0 minus 1 0 1. So as a result of this operation, you are going to get, here you will get 0 and here you will get 1. So you will have minus 0 1. That means you will have just, there is a phase change would be there. Okay, so this is what. And similarly, what about Y gate? Y gate is defined as 0 minus 1 1 0. That's the Y gate. And now if Y gate operates on K0 state, it would become, okay, let me do it, 0 minus 1 1 0, and K0 is 1 0. So you are going to get it to be, you are going to get it here 0, okay, and this is going to be 1. So it is going to get flipped. K0 is going to get flipped to 1, and if it operates on 1, you will get 0 minus 1 1 0, and this would be 0 1, and it's going to become, you will get minus 1 here, and here you will get 0. That means you have minus 1 0. That means it is minus kth 0. So again there is a phase change here. In this case, kth 1, when y gate operates on it, you are going to get kth 0, but with a phase change would be there, with that's the reason minus is appearing here. So with these results we are having, now we can clearly see that when this is our input to the z gate, what we are going to get is this. We are going to get 1 by root 2, 0 will remain 0, and 1 will remain 1, because this is identity. Second one, I am talking about this first term, and similarly for the second term, I am having 1 is now going to become minus 1, right? It's not going to get flipped, only there's a change of sign, 1, and 0 will remain 0. So this is what you will have. Okay, so let me now draw the circuit once again. So we have here this Hadamard gate, okay, and followed by this C0 gate, okay, and then we have here this Z gate, and then we have also this Y gate. Z gate is operating on the first qubit, Y gate is operating on the second qubit. Now after this Z gate operation, okay, after this C0 gate operation, what we have got, we got the state to be like this. It's a superposition of 0 1 and 1 0. So we have here 1 by root 2, 0 1 and 1 0, and therefore here at this stage we are going to get 1 by root 2. By the way, Y gate is going to operate on the second qubit, right? Second qubit. So therefore output, and the Z gate is going to operate on the first qubit. Okay, it's going to operate on the first qubit. So therefore the resultant state is going to be 1 by root 2. You are going to have here 0, and 1 is going to become, because Y gate is operating on it, so 1 is going to become 0, okay, and is it correct? Y is going to operate on 1, you see it's a minus. This is what you will have, and Z is operating, if you look at the second term, Z is going to operate on the first qubit, 1. So if Z operates on 1, so it's going to become minus 1. So therefore you have here minus 1 here, and when Y is now operating on 0, it's going to become kth 1. So this is what you are going to get. So overall, that means I can write that the output state, overall output state is going to be minus 1 by root 2 kth 0 0 plus kth 1 1. Okay, so this is the final output state after the quantum circuit. So at the input you have given 0 1, and at the output you are going to get this particular state. As a final problem of this session, let us work out this problem. Now here you are given this quantum circuit. You are asked to find out the output state if the input state is 1 0. Now if you look at this quantum circuit carefully, you will see that there are two C0 gate. This is the first C0 gate, this is the another C0 gate, but this middle one is not actually the usual C0 gate. It is actually inverted C0 gate. Okay, it is also a C0 gate, but now in the inverted one, inverted C0 gate. So let us work it out, and when I will explain, you will understand how the inverted C0 gate is going to work. So let us do the analysis systematically. So first of all, you are having the first C0 gate, and your input is said to be 1 0. So in the first qubit is 1, so second qubit is 0. When it passes through the C0 gate, the first C0 gate, what it is going to get, you are going to get the output is going to be, you see now here your control is 1 and target is 0. Now because the control is 1, this is your control and this is your target. Because your control is 1, the target is going to get flipped. So here you are going to get 1 and 1. So this is going to be basically your input for the second gate. Second gate is now a inverted CNOT gate. Now inverted CNOT gate is basically what is going to happen here. This will act like a control now, and this is going to act like a target. So the operation is exactly going to be the similar. So because the control is 1 and target is also 1, so the target qubit is going to get flipped. So at the output here you are going to get control will remain as it is 1, but the target is now going to get flipped, it will become 0, right? So this is what you are going to get at the output after the inverted CNOT gate. Now this is followed by the usual CNOT gate, so therefore you are having this one. Now here the control, this is my control is 0 and the target is 1. Okay, because the control is 0 and target is 1, the target is not going to get flipped and you are going to get 0. So you are going to get 0 1. So overall what you have basically seen is that your input is 1 0, and then when it is passes through this particular quantum circuit, at the output you are simply getting 0 1. Okay, so this is how you can analyze all kinds of gates and quantum circuits.